Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Marynel Vázquez, who is an assistant professor in Yale's computer science department. And there she's the leader of the interactive machines group. So something about Marynel, she obtained her bachelor degree in computer engineering from the Universidad de Simón Bolívar in Caracas, Venezuela. She then moved to the US, where she obtained her Master of Science and PhD in robotics from CMU. And there she was also a collaborator of Disney Research. And then she spent some time as a postdoc at Stanford, and then she joined Yale. In her group, she focuses on human-robot interactions, especially in situations in which you have multi-party and group settings. And as you've seen in the bio for this, she has been awarded a number of prizes. I mean, the research is very exciting. And today she's going to talk about a few stories of when our HRI assumptions were wrong, the challenge of social context awareness. And I'm personally very excited to hear more about it. And therefore, I give you the stage, Marynel.
Thank you so much. I'm very happy to be here. Apologies for all of you in that, sometimes my head is going to look that way, but I know you're expecting me to look that way. I have many monitors here. And so I'm still paying attention if I'm looking that way for whatever reason. Now, today I want to talk about human-robot interaction, and I know not necessarily everybody works in this field. And so I thought it would be kind of fun to start by telling you on sort of at least two stories of things we assumed that didn't quite go the way we were expecting, and why I think in many ways this has motivated a lot of the work that we're thinking about today. For context, as you said before, I'm at Yale, and a lot of what I'm presenting, however, is a mix of work that I have done, sometimes in collaboration with other people, and so I'll make sure to thank them at the end. And so when you think about human-robot interaction, this is for the most part what comes to mind. And a lot of the work that we and other people do in this field sort of focuses on understanding how people perceive robots and how we can best design interactions for them. And this is very important because, well, for the most part, even though oftentimes people interact with robots in a similar way as they would interact with humans, there's many cases where they don't, and we sort of want to understand what are those factors that change things, or what opportunities arises when we have these machines in the world interacting with humans. Now, I want to show you one sort of particularly cool robot, in my opinion, that we have been working on recently, that we pretty much approached from a very classical user-centered design point of view. This is Omi. This was a robot that was designed by Kayla Matthews, who's a student in the social robotics lab here at Yale. And we've been collaborating with this lab to sort of push forward this robot over the last few years. Now, let me explain what this robot is. Hopefully, you're going to see it moving a little bit in a second. So this is a robot that is very simple. It looks like a ball. It's a social robot, right? Clearly has eyes, and is meant to engage you through that in an interaction. But more importantly, this is a robot that hopefully can help you relax. And it was designed to help people with anxiety. And so what the robot is meant to do is, at least to start, guide you through a set of breathing exercises. And the way it does that is by sort of simulating that it's inflating. This is not actually inflating. In fact, it's actually a servo that is inside that makes it move a little bit up and down, but then it actually feels like as if it was breathing alongside you when you're practicing deep breathing. Now, to make this robot, in many ways, we followed a typical approach where, we thought about, okay, this is the space that we're working in. What in general would we want to enable in this space? And then to validate it, we went and conducted experiments that followed this pipeline that you see here. So we go and design a user study and what kind of robot behaviors we want to test. We collect data, perhaps we filter data, and then we analyze sort of what remains. Now, you may wonder why is there a filter data step? And that is, well, because oftentimes we make assumptions about how interactions are going to work, especially in our very controlled laboratory environments. But, well, sometimes everything doesn't quite work out the way we expect. And so it is the case that sometimes we sort of perhaps focus on analyzing a subsection of the data or perhaps certain aspects, not necessarily everything that happened. Now that process as a whole has got me thinking oftentimes about, well, what did we assume and what things didn't quite happen the way we were expecting. And so I'm going to tell you two stories about this to motivate the second half of my talk, which, as you'll see later, is really focused on a fundamental question in HRI. And so the first story I want to tell you is about a furniture robot. And for this, I'm going to go back now many years when I was a PhD student at CMU. And at the time, I got the opportunity to work with Disney Research. Now, Disney wanted to have at some point a robot that looked as if it was sort of coming out of this world of the Beauty and the Beast. And so we ended up working on making what we called at that point in time the furniture robot, which you see here. This is, by the way, a picture. This is not a render. This is actually how the robot looked at the time. And so this robot, as you can tell, again, is a social robot. It has very clear eyes and mouth. And interestingly, we could actually turn the lamp on top of it into a second character, which we sort of tested. Could that help move the storyline along when we're having interactions with children? And so I'm going to show you a very brief clip of what an interaction with this robot looked like. Hopefully you can hear, but if you can, for whatever reason, let me know, because it's useful for me to know if audio is not working. So let me show you.
Hello, I'm Chester, the coolest piece of furniture in this office. And
he real?
Is my friend.
It's a robot.
So this was sort of the very initial part of the interaction. These children had come to the lab not knowing that they were going to interact with the robot, and then they sort of found it. And the goal of the robot was to give them a small souvenir as a result of having come to the lab at that point in time. Now, I thought when I designed this interaction that these children will be engaged with the robot all the time. I mean, it's a robot that they were not expecting. It was there to give them a souvenir. That sounds all kind of very fun and new. The reality, though, is that I was wrong. Okay. What really happened was that the context of that interaction often changed depending on sort of what happened along the way. And so, for instance, in many cases, we had the members of the conversation with the robot change. Originally, I thought it would be all of the children that had come to interact with the robot, but you can see here in this case, out of 4 people, we ended up having 1 that was really engaged with the robot towards the end of the interaction, even though the robot still had things to say to them. Even more new conversations started right in front of the robot. And for the most part, the way I had designed the whole script for the interaction did not assume that this was going to happen. So the robot didn't have any way to sort of acknowledge the fact that other things were happening nearby that it was actually not part of. And this, for the most part, motivated a lot of my PhD work at the time, trying to figure out how do we enable robots to recognize these group interactions. Now, I'll talk a little bit later on sort of technical approaches that you can use for this problem, but I want to switch gears now to a second story where I would say, again, similarly, we sort of made wrong assumptions when we started. Now, the context of this story is a little bit different. So for a couple of years now, I have been interested in understanding prosocial behavior. How can we have robots motivate humans act in prosocial ways, basically act in ways that help others without necessarily being something that they would naturally do, or perhaps something that costs them in some sense, some effort or poses some cost to them. Now, on the other hand, we have also been thinking about what if we make robots such that they generate prosocial behavior, meaning when people interact with them, people perceive them as like, wow, you're helping me. I didn't expect that, because that doesn't seem sort of the rational thing to do at that point in time. And so to test out this particular idea, this was during COVID. And so we decided to do an online study where we had people play this game of Space Invaders with an agent. And so here, the purple spaceship is a human-controlled spaceship. And then the orange one is one that was an autonomous sort of AI-driven co-player. Now, in the context of this game, the human will get points for destroying enemies on the left side of the screen and the other autonomous co-player would get points for destroying enemies on the right side of the screen. Now, what we did was, at a certain point in time that people were not expecting, we had that co-player go to the human side and quote unquote help them destroy enemies, which we thought would be sort of the simplest description of prosocial behavior that we could implement in this toy environment, right? And why is this prosocial? Well, instead of getting points for yourself, the autonomous co-player is going and giving points to the human. Now, as you may be expecting, or maybe thinking, well, not everybody considered this behavior as quote unquote helping. There's some people who are like, wait a second, why are you coming to my side? I want to destroy my enemies. This is my part of the game. You stay on your side. Other people were more like, oh, please come over here because this is very hard. You know, I really need help. Whenever you want, just come over here. And so we thought, oh, this is very interesting, right? Like if you assume sort of the naive setup where, oh, just maximizing the human's reward and that corresponds to helping, well, sometimes you're going to be wrong. And so probably this agent needs to learn as it interacts with people, what does it mean helping, to help them specifically, right? Because people may have different preferences. And so thinking about this, we thought, well, how can we enable this agent to enable preferences? And one idea that came to us based on recent work in HRI was that, well, perhaps we can analyze human nonverbal behavior as they're interacting with the agent and make a prediction out of that in terms of whether they're liking what's going on or not. And so this is sort of how things typically work in HRI when you think about using, say, facial reactions for this purpose. So you would have, some observations, which I'm calling here S, of the human, like, maybe this is facial action units or something that describes sort of how they're reacting. And then you typically use a function to map these observations to some description of the expressions or emotion. And oftentimes this function is not something that we necessarily sort of come up with in HRI. There's a lot of work that has studied this problem in affective computing. And so it is also often the case that we use some pre-built model to create this mapping. Now, once you have that expression of emotion, then the typical thing we do is we now map that to some reward for the robot or maybe some preference, right? And so you say, oh, if the person looks happy, probably that means that the agent is acting well, so good robot. If the person is maybe not looking as happy, well, maybe, we do the opposite. Maybe we say, oh, this is some kind of behavior that the person doesn't want. Now, we came into this project with that model, and here's an example of how someone reacted while playing the game. This is, by the way, videos that we captured with users' permissions while we did the prior study that I showed you. Clearly, this person doesn't look very happy. And so the naive thing you would assume is that, oh, probably the agent is not doing the right thing. But when we went back and we looked at, what was going on here in the game, what actually happened in this point in time was that the spaceship of the human got destroyed. And so a bullet hit their spaceship, therefore they reacted this way. And this naturally sort of brought up to this context the importance of paying attention of what's happening in the task. If this is a task that, the human is not just observing, but is actually taking part on. And so this assumption that I had, can we predict how people perceive an agent? I think in general is a hard problem, but it is possible. The key to this is that you cannot just ignore everything else that is happening and just analyze sort of, the person's reactions. You actually have to analyze these reactions in the context of the task that is going on. Okay. And so before I move on, hopefully, with these two stories, you start seeing that even though in many cases, in even our very controlled environments, the assumptions that we make don't quite work. And that is because this context, although we try to constrain it, is still very complex. And so this naturally brings up the question of, probably if we want to advance autonomy in all of these setups, what we really need to be thinking about is how do we enable robots to be aware of this social context? And so I'm going to pause for a second and see if anybody has questions about the two stories I just told you, because I'm completely going to switch gears and talk a little bit more about, context and perhaps how we may think about it in HRI before I move on. Perfect. Okay. So let me continue and let me now get into this question of, well, what is context? This is actually a great question because context is a very overloaded term. And so, you know, if you work in, for instance, NLP, then you think about context as, you know, many tokens that perhaps precede something that you're trying to reason about in a sequence of tokens. Context has been used in many other domains like physical robot manipulation to reason about, you know, where objects are and things like that. And so I want to bring to attention some ideas that people have been using in the context of HCI first to think about context. And this is work in particular by Anin Day, who at the time when he was a student, he started to try to formalize this idea of context, in particular for ubiquitous computing. And so at the time, Anin thought of context as any information that can be used to characterize the situation of an entity. An entity is a person, a place, or object that is considered relevant to the interaction between a user and an application, including the user and applications themselves. Now, clearly, you don't see here specifically the notion of robot, because that's not what Anin was thinking of at the time. But I think I like this description in that it starts enumerating many things that may matter to us when we think about context. Now, more recently, in the context of human-robot interaction, Laurel Rick studied this question in particular for mobile robots. And they had these robots sort of navigate across different places on campus to try to see how we could perhaps start modeling social context for this robot. Now, in this work, context was defined as follows. So we defined the social context for a robot, P in this case, in a given environment E as the union of several subsets. And so we have the situational context as a function of the environment, the social role of the robot in the environment, and a variety of norms that dictate how the agent should behave and how that environment typically sort of operates. Now, in our work, we have like this idea of thinking about context, especially focused on robots because, well, we care about HRI. And because of the two prior works that I showed you before, I think it's very clear that the environment plays a key role here. Now, we started thinking about this problem in social robot navigation. And one of the things that you often notice in this space is that a lot of the work is very focused on studying how a robot moves around a certain group of people in sort of one particular interaction scenario. And going back to some of the work that Laurel was doing before, I think it's important to recognize that really the way that the robot perceives the environment and how it should behave is strongly sort of biased or dictated by what that scenario is. And so we decided in this case to start thinking about context in terms of social situations. This term social situations, by the way, we borrowed it from the psychology literature. And what social situations are basically the composition of what a human is doing, in our case, what the task of the robot is, and what other people nearby are doing, which typically in navigation would be sort of pedestrian behaviors, plus sort of information about the physical environment where all of this is taking place, because at the end of the day, these are collocated interactions. These are situated interactions, as other people call them. And so in social robot navigation, one early work that we did was defining all of these different scenarios that you see here that are very common for navigating human environments in terms of simple logical descriptions that allows us to identify them in sort of complex, crowded settings. And even more, we decided to create software to generate this type of scenarios, thinking about all these different components that I mentioned before. This video that you're seeing now, this is what we call the social environment for autonomous navigation. And is an environment that you can use to prototype mobile navigation behaviors in Unity, and everything is connected to raw so that you can actually run your controller sort of the same way you would typically run it on your robot. Now, this graph that you see being created here, this is sort of a graphical user interface that we define to allow for people to very quickly set constraints on how crowds would move across this environment, where basically the nodes would be places where the people that navigate as part of this crowd are going to change directions, and then the edges connect different places that they can navigate through. There's specifically certain special nodes in here that allow you to also create group formations that are typical of sort of multi-party interactions. And that is just to add more diversity to how people move around. Now, in particular, in this case, now you can see here sort of people moving according to that graph. Everybody here is moving using a combination of social forces model, which where the forces that are defined by the graph that I showed you before, plus a very simple low level controller to make them look like they're walking, make things a little bit more realistic. And I'm here just showing you how you can simulate different sensor data, right? You can have like depth images, or you can also sort of connect things, as I mentioned before, to the ROS navigation stack. And so in the bottom, you can see a map of what the layout of the environment looks like in Arvis, where we're keeping track of whatever the robot can perceive. Now, the big benefit, right, of starting to think about context and trying to formalize and generate a way to create context is that now we can more easily evaluate navigation behavior across these different scenarios in a systematic way. And so thinking about context helps us understand where is the navigation sort of working well, or maybe where it's breaking, so that we can focus our efforts on understanding better the behavior in those situations. Now, importantly, the sort of different types of social situations that we can generate in Sean are not exhaustive. And more recently, we have started to work with a lot of the community in the social navigation space to think more broadly about what other types of situations may come up that are worth studying and analyzing in practice. And so if you want to know more about this, I encourage you to read this paper that we recently put in archive that shows all the different scenarios that you see here on the right. And I think we'll be very interested, if you're working in this area, to try to sort of formalize additional benchmarks for this space, so that we can all sort of measure progress as a community, rather than sort of each of us making our own thing, where it's really hard to sort of know how well we're doing. All right, now, given what I said before, I really like this idea of sort of thinking about these scenarios, especially for navigation, because the structure of the task sort of makes it very, very natural to think about all these different situations. But more generally, just thinking about it or trying to define it the way we did before, for instance, in terms of logic, is actually very limiting. And there's many more things that I would like to encode in these sort of context models that perhaps sometimes you don't get to see so much in navigation, but may come up in other applications. And these are in particular, for instance, group social phenomena that may come up in other types of multi-party interactions that I think would be interesting to model as well. Now, to get to that, I wanted to show you this relatively recent review of robots in groups and teams by Tarasivo and collaborators. And I like to show this when I describe thinking about context, because it sort of breaks down how one may think about group interactions in HRI from an input process output perspective. And certainly here you can see that context is a lot more than what I've mentioned before. And so, for instance, in terms of the inputs, you have the things that we have talked about, like human factors that matter to these interactions, robot factors that matter, or environmental level factors. But then again, there's also these group level factors that play a key role on what's going on. Now, on the output side, as the interaction is progressing, then maybe you care about many different things that also change how robots should be perhaps behaving, or how they should perceive what's going on. And here, for instance, you may have task performance outcomes, but also perhaps you care about how people perceive the group or how people perceive the robot. And so I've sort of, in many ways, started to think about context a little bit more like Anin thought about it, as a collection of things. But we're now sort of expanding to everything we think could matter in the context of situated interactions. And these are sort of all of the factors that I showed you before. So we want to consider individual factors, things like who is this person that I'm interacting with, what are they saying, sort of unique attributes about them. We also want to consider pairwise relationship factors that can be, for instance, low-level communicative signals that maybe people exchange between each other, but potentially can also be affiliation. It can also be perhaps are they interacting together, as in the example I showed you before. And then there's higher level group factors that also matter, and of course we're again collocated in the environment, so the environment plays a key role. And so the sort of big picture idea now is, well, how do we computationally model all of these many things, which in many ways sort of seems like a combinatorial explosion of elements. And the typical way we would go about this in HRI today is that we create, and what I'm going to describe as simple mathematical models for the part of the context that we care about. Now, simple is not necessarily a bad thing, right? There's value in simplicity, but I want to point out that they're often simple because we're coming up about them with sort of heuristics, building on a lot of the work that you typically see in psychology, and trying to formalize that in one way or another, depending on the specifics of what we need. And so to give you an example of this, going back to the furniture robot during my PhD work, the way that interaction changed, it motivated us to work on detecting conversational formations. And to do that, we went to sort of what I would describe the main reference of this work in psychology by Adam Kendon, and then create an algorithm to detect them. And so this algorithm would say, well, everybody in a scene has what is known as a transactional segment. This is just the space in front of them that includes whatever they're engaged with, according to Kendon. And what happens is that when they converse with one another, they intersect this transactional segment with each other. And if that happens, then a group will be formed around the shared region, which is called the O space of the formation. And so whenever our algorithm found an intersection between people's transactional segment, it say, aha, a group must be happening there. And probably the people that belong to the group are those that are sort of intersecting the transactional segment with the O space. Now, at the time, this was great because I could finish my PhD by demonstrating that a robot could detect group interactions in real time. This is shown here with the polygon on the ground, despite, in this case, having very noisy human observations. You can see here, for instance, the person in yellow, it looks like they're raising their arm in our Kinect measurement, but clearly they're not raising their arm in the video that you see here. And so I was very happy, right? Because I could have my robot test different gaze behaviors and different orientations behavior with this group in an autonomous manner. But it was also very clear to me that, if I wanted to translate this algorithm to a bunch of other scenarios, well, it's just not going to work, right? It's not going to work because it's completely ignoring a lot of the things that potentially change the way that people use space nearby each other. Like, for instance, maybe they're engaged in some activity that requires them to queue behind one another, or maybe they enter a really tight space where, maybe now they're okay being very close to each other. And that was not something that my algorithm sort of typically would consider. And so this sort of made me realize that, well, I think we need more flexible and generalizable approaches. And here I think machine learning sort of offers a lot of opportunities to think about how we should start modeling context for HRI. Now, the standard way we think about machine learning is sort of focusing on the model. But I want to make the case here that we really need to think about all these three ingredients that you see here. And so how would it typically apply machine learning to HRI? I'm going to give you sort of the prototypical scenario. So if we have, two people interacting with a robot, what we do is we compute some features for them, we concatenate them, and then we pass them to our favorite model and make a prediction. If you have some labels, then this is, supervised learning, and it can work for a lot of different things. For instance, in this picture that I show you in the right with collaborators at KTH, including Sarah Gillette and Yolanda, who I see here, we were actually using this type of model to control the gaze of the robot and try to influence how much people were talking to one another in these interactions. Now, this works great, right? If at the end of the day, everything stays like what you see in this picture, meaning all of your assumptions about what the interaction is going to look like is constant and remain true throughout the interaction. But imagine that suddenly, a person opens the door of that room and now wants to join the interaction. well, my model doesn't really work anymore, right? Like I have one more person and now I need to consider that, you know, they have their own features, but my model was not trained with that many features. And so a lot of sort of hacky approaches end up coming into play to make sure that, you know, your model can still be reused. And this sort of made us think, you know, principally what kind of abstractions are the right abstractions that we should be using to model these interactions before we sort of jump into the models. And so for a lot of the work that we're doing now, we're thinking of modeling these interactions as relational data, because at the end of the day, we care about sort of how humans interact and sort of change their behavior with respect to robots. And that naturally brings you to a graphical representation like what you see here. Now, this is, of course, not a new idea. Graphs have been used for a really long time in many other related areas like social network analysis or even multi-agent systems to analyze the interactions between many agents. And I think to me that's a positive, right? Because that means that in HRI, we can now start bringing methods from those areas to try to improve autonomy for robots in these types of social settings. Now, this is not to say that there aren't interesting things that come up in this graph, and I want to mention a couple of ones in the context of HRI. So first of all, in my opinion, oftentimes, because we have co-located interactions, the graph that we're going to use to represent the state of the world at any one point in time is probably best if it's a fully connected graph. Okay, and the reason for that is that even if people are not explicitly interacting with each other, the fact that they're sharing space with each other means that they can potentially influence one another. And that probably, to model that, then you're going to need sort of a fully connected graph. Now, the other thing that is interesting about this graph, because we are in sort of a robotics context, and all of the data that we're going to use to build these graphs are effectively going to come up from observations of the environment, potentially observations that the robot is gathering from its own sensors. And so what that's going to do is that we're going to have a lot of features for people. We're going to have also potentially a lot of features for the edges that describe pairwise relationship factors between all of these different agents. And additionally, I have drawn here a global graph attribute to encode that we also probably are going to have some additional features that describe the environment when we reason about the connectivity between these elements. Now, one nice sort of artifact of thinking about things as graphs is that naturally we can start thinking about how a robot may be influencing people. And again, as I said before, I think there's a lot of work from social network analysis that we can perhaps start to take advantage of in these HRI settings because of this abstraction. Now, going back to the question about models, there's a variety of models that you can use to reason about these graph abstractions. Generally speaking, oftentimes, if you're thinking about state-of-the-art deep learning methods, you're going to hear about them being described as graph neural networks. And these are the class of methods that I think we should be sort of paying more attention in HRI because of that abstraction that I described before. And you can think about them as, you know, data-driven methods that for the most part are structured. They're trying to leverage the relational structure of that graph in order to make suitable inferences. Now, there's a variety of graph neural networks that exist today. And I want to talk a little bit more about one particular class that I really like, and I will explain why that is the case, okay? And these are message passing graph neural networks, which I'm very curious, how many of you have heard about message passing graph neural networks? Can you like do thumbs up if you know what they are? Have you used them for something? No, excellent. Okay, so let me give you the 101 of how this works. So these are neural networks. It's actually a collection of neural networks that what they're going to do is they're going to transform a graph, G, that you see here, into another graph, G prime. And you can apply them just like you apply, you know, recurrent networks, and you can stack them. You can do the same thing here and sort of transform the graph from some representation to some higher level representation as you stack them together. Now, ultimately, what you're doing is computing new features for your global graph attribute, new features for your nodes, and new feature for your edges when you apply these neural networks. The way you're going to do that is as follows. First, you're going to use a differentiable function to update the edge features in your graph. And so for every edge, you're gonna take information from the nodes connecting to it and from the global graph attribute and compute a new representation based on that information. Then you're gonna update the node features in all of your graph. Now you're gonna take all of your updated edges for any node that has edges that sort of connect to it. You're gonna summarize the information coming from those edges using typically a permutation invariant mathematical operation, things like averaging or maximum, things like that. And then given that summary, you're gonna also compute a new representation for the node given the prior node feature that you had there and your global graph attribute. And then finally, the update for the global graph attribute is going to take information from all of the nodes and the edges and the prior global graph attribute to then compute a new representation for you. And this is all happening with differentiable functions, so you can back propagate through all of these three operations to effectively compute the new graph that I'm displaying here. Now, the reason why I really like this type of framework for reasoning about the graph data that I showed you before is because the update that I mentioned first, updating the edge features, if you add supervision at the edge level, you can effectively use this type of framework to predict relationship factors in the social context of the robot. And so I'll show you an example in a second where if we add supervision, for instance, for who's interacting with whom in a given time, then we can predict group interactions like the ones that I showed you before with the robot at the beginning. Now, if you add supervision in the node level, then you can use this operation, this second operation, to predict individual factors that matter in the context. And I'll show you some examples in a second. Now, similarly, if you add supervision on the global graph attribute, then you can actually consider the whole graph to make predictions over groups. And this is sort of a very nice way of now putting together all of the many different things that we often care about when we think about the social context of the robot and thinking about them all from a unified perspective. And so my hope is, in the future, instead of each of us sort of coming up with our very specific siloed way of representing context, perhaps if we start encoding all of this information in a well-structured manner, for instance, in a graph, and we start using these data-driven methods that give us a lot of flexibility to sort of adapt predictions based on the complexity of these interactions, then hopefully in the long term, we're going to be able to build better models for robots to understand what's happening around them. And so that's sort of the vision for the future. Now, in recent times, we have started to use this idea to study a couple of different problems. This speaks in a way to the generality of this framework. For instance, as a result of the furniture robot experience that I showed you at the beginning, we have done a lot of work on trying to predict who's interacting with whom and detecting group interactions. I'll show you kind of a little bit more explicitly how that looks like in practice in a second. We have also tried to predict individual factors like who would like to interact with the robot in the near future before they officially interact with it, so that the robot can take proactive actions to perhaps better engage that person. We have also tried to predict specific behaviors for a robot as a function of what's happening in a group. And again, now we're making a prediction for the robot in this context. And more generally, we have also tried to reason about groups as a whole. And so it's kind of interesting to see that at the end of the day, despite all of these different problems being very different, all related, of course, to modeling social context, the same sort of underlying approach applies as well. Now, given that I have limited time, I want to tell you just one interesting story of one practical challenge that you may have applying these models. And we started to think about this when we started working on applying this type of graph neural networks to the context of group detection in HRI. And so here the approach is relatively straightforward. So imagine that in a socialist scene, I can detect a number of actors, say here, these people that you see here. I can build a graph for them, and then I can use a GNN to predict for every edge, are these two actors part of a group conversation or not? Okay. And if you have supervised, if you're in a supervised learning setup where you have labels for this, then typically we would apply, a cross entropy loss on the edges where we try to distinguish, are these two agents part of the same group or not? Now, depending on the data that you're using for this, if you have a highly imbalanced data set where maybe, most people are not interacting with each other, or maybe most people are interacting with each other, then just using a standard cross-entropy loss without much care for how the data is balanced would effectively often let your model to predict, everybody's interacting with everybody all the time, or maybe nobody's interacting with anybody. And so then you have to sort of start thinking carefully about, how your batches for learning are structured so that hopefully, well, you have a roughly equal number of samples per class. And now the tricky thing is that one example is not one edge. Actually, when you apply these GNNs, one example is a whole graph. And now if you start thinking about how do you sort of maybe balance these graphs in your batches, then things start becoming a lot more complicated. And so one of my students, when we were working on this, he asked, wait a second. So, at the end of the day, we don't really care about how well we do in a cross-entropy loss. We care more about how well we do overall, for instance, with a metric like the F1 score. Why aren't we directly sort of training our model on that so that we can hopefully identify when the model is making these very bad predictions? And well, it turns out that doing that is not so trivial, okay? And the reason is as follows. Typically, if you have some input, say in this case, a graph, and you're using a neural network like a GNN to predict things for all of the edges, where here I'm just focusing on one edge, then to turn that into some metric for classification, you first have to convert the probability output by the network to a 0-1 prediction using a Heaviside function. And this Heaviside function is actually a bottleneck it's actually a problem for backpropagation. Why? Because the gradients are 0, undefined, and 0. And so you cannot sort of so easily propagate errors back from F1, for instance, or all the way back to the parameters in your network. Now, what we realized, though, is that if you actually approximate this Heaviside function, for instance, with a piecewise linear function or a sigmoid function, then you can actually train these GNNs more easily when you have imbalanced data. And you do this by basically computing your loss on close approximations of the metrics that you actually care about. And so if you are working on, some binary classification problem using this type of networks, and it happens that you have heavy data imbalance, I encourage you to try out this approach. You can very easily install this with pip. If you follow this link, you'll see all of the details. Now, the last bit I wanted to talk about today is the need for supervisory signals. And it's not just that we need some signal. Generally, we actually need a good signal to make these models learn well. And so the typical way we collect this data in HRI, as I mentioned before when I started my talk, is via user studies. And we do this in a very experimental manner where we bring people to our lab, and then we get some data, and then we try to build models out of that data. But of course, that leads to very scarce data in practice. And so this has motivated the community to think about how we can scale data collection in human-robot interaction. And one way you may think naturally of doing this is by taking advantage of the internet, right? For instance, using crowdsourcing to get a lot of information from people that observe how a robot is behaving, and then using that to build potentially better models. And so, for instance, here are 2 examples of specific systems that have been built to potentially take advantage of the crowd in robotics scenarios. Now, the tricky thing with all of these setups is that each of the different solutions that people have built to deploy these different environments on the web is sort of very specific to that simulator or that set of tools that you're using. And so when COVID hit and we wanted to sort of deploy more things on the web, we asked, well, what if we want to now deploy, for instance, our Sean simulator that I showed you before, which is a very client-heavy simulation on the web, and then sort of make sure that all of the ROS components that we have can run in parallel to that? Well, this is not as easy as just exporting the game with the plugins that Unity provides, because, again, we have all of these ROS components under the hood that we need to control an agent in that simulation. And so what we ended up doing was actually building a tool that we call the Sean experimental platform to more easily allow to deploy these complex client-heavy simulations on the web and then use them to get data for HRI. The way this works is relatively straightforward if you're a savvy Linux user. And so what we do is we take the simulations, all of their complex system components, then package them into a Docker container, and then use standard programs for graphical desktop sharing in Linux to export the graphical user display from that simulation onto the web. And because this is made for desktop sharing, you can also get back into the simulation input from the user on the web. And so with that, we can potentially scale data collection by scaling both within a machine or across multiple machines and have many people sort of connect to the simulations in parallel. And so just to show you how this would look in practice. So, you could have in a website, you can have this Sean simulator that I showed you before, where someone can now, for instance, interact with the simulation by controlling an avatar in it. And then you have this robot in the backend that is controlled by the robot operating system. But people don't need to know anything about this. They don't need to know about ROS. They don't need to have a heavy GPU because all of this is happening on the cloud. All they get to do is sort of interact with the simulation in a very natural way without having heavy dependencies on their machine. Now, if you worked in HRI, you're probably wondering, wait a second. So we can get data through these interactive simulations, but how well would they be relative to the real world? Because at the end of the day, right, we care about robots performing well in the real world. And so we've started to do some experiments to try to evaluate this. This is, for instance, in a scenario where we had a person interact with a mobile robot that you see here in my lab. And then we modeled my lab and then had people do the same task in the Sean simulation that I showed you before, so that we could get data of, what do people think of the robot in the real world versus what do people think of the robot in the simulation. Now you can see that the simulation is not perfect. And so we thought, well, maybe the results are going to be biased by how the simulation looks. And so can we, in a way, disentangle a little bit how the look of things are versus what kind of data we would get if we were to do this study using videos of the interactions, which is in a way the most standard way you would evaluate. You would get data through crowdsourcing in HRI. And so we ended up making videos for both of these conditions where now we ask people, what do you think of this robot in these interactions in video that were done in the real world? And what do you think about it in simulation? Now, don't have much time to go over all of these details, but I want to highlight that based on the results that we got, neither the simulations or the video potentially get you 100% to what you get to see in the real world. Potentially, though, the interactive simulations may approximate more often the real world than videos, or at least that was our experience based on the results from this study. Now, because the real world is sort of at the end what we really care about, a lot of the other efforts we have been doing in my lab have to do with deploying robots on Yale campus, where we can hopefully see these multi-party interactions happen in a more natural manner. For that, we built this platform that you see here that is Shutter. If you're looking for a robot that you can use to study HRI, this is all open source, and so you may actually build your own robot as well if you want. All right, so now to wrap up, I have talked today about social context modeling, and I think one of the ideas that is driving a lot of our work today is that we should leverage graphs abstractions in HRI and relational models. Now, there's a lot of things that I have not talked about that I think are open questions in terms of how do we incorporate them into these representations and models. And so, for instance, a lot of the work that you see in HRI explicitly accounts for a theory of mind, and I think it would be really interesting to extend these models with these ideas. And last but not least, I kind of ignore social norms, which prior HRI work had mentioned as an important aspect of the context, and I think combining these social norms with these representations is particularly relevant moving forward. Last but not least, graphs are used for many other applications, and I think is very interesting to think about how we can combine the social graphs that I've shown you today with other types of graphs abstractions in robotics. And so, for instance, we have been used topological maps, which are graphs that describe physical space for navigation, and it would be really interesting to combine these graphs for physical space with the social graphs that I've shown you today. And so to end, I want to thank all of the people that have made this possible, especially including many of the students that led these projects and our collaborators at other places. And of course, also the people that funded this work. And I'm happy to take any questions. Thank you.
Thank you, Marynel, for the great talk. Let's open the stage now for questions. You can either unmute and ask or post in the chat and I can read the question for you. So who wants to be the icebreaker? Oh, Alessandro, go ahead.
Thanks for the great talk. I'm not experienced with graph neural networks, but when you use them to model the relation between agents, and you have clearly these relations that as the robots or the human moves, they change over time. How do you deal with, let's say, the topology that is dynamically changing?
Yeah, so today I would say the standard way of dealing with this is with sparse tensors. And so this is something that is not something we came up with. This is something that is often done in machine learning, mainly because, you know, it is often the case that you have graphs with different number of nodes and different connectivity. And how do you sort of group all that together so that you can pass it to your GPU and then apply, you know, operations over there. And so the trick oftentimes is that the batch will basically be a humongous matrix where sections of that matrix will correspond to a different graph. Think about them sort of laid out along the diagonal section of that tensor. And then everything else will basically be, you know, zeros, no information. Now, because there's a lot of empty space, you don't want to use regular tensors. You kind of prefer using sparse tensors so that, you know, in terms of memory, you don't run out of memory very, very quickly. Now, the other thing that I was going to mention that is important for HRI that is a big headache from an implementation perspective. And that is that, you know, if you want to reason about things over time, you have to make sure that you can, in a way, know, oh, this node at time t-1 is actually the same agent at time t, and so on and so forth. And so here I'm assuming for a lot of the work that we do that you have in many ways some way of figuring out who's who. and we're not necessarily sort of embedding that also into the problem of encoding the social context. And so that is a problem that we're assuming, you know, you can resolve with, you know, maybe some people trackers or perhaps with, you know, information about, you know, your robot or maybe the other robots that are in your environment. Does that answer your question?
Yes, thank you very much.
Actually, I had a question which was related to the one Alessandro asked, maybe to complement it. At some point you mentioned that these graphs typically in your applications need to be fully connected. Is one of the reasons also the fact that the interconnections might change over time? And if you assume fully connected, it means that you can always change the attributes over time while keeping the same graph? Is it one of the reasons?
So let me clarify one thing. So fully connected at a given time step, but not fully connected across time, which is very important difference, right? And so, you know, over time, I think really the most important connection is that, you know, oh, this is the robot, and before this was the robot still, and before that this was the robot still. And so you kind of need that connection between the nodes that correspond to the same agent. Now, the reason why you want a fully connected graph on a given time step is a little bit more fundamental from a theoretical standpoint. So in psychology, a lot of people have argued, you know, what's the difference of, you know, me talking to you versus me passing next to you when, you know, there's a narrow hallway. Are these two interactions? Because, you know, in one case we're like exchanging ideas and we're both focused on each other. In the other one, well, we're sharing physical space, but maybe we're not explicitly exchanging communication. At the end of the day, both of these type of events are interactions. It just happens that one type is an explicit interaction, the other one is an implicit interaction. No matter what, though, your behavior, if you're there and I'm there, is going to influence each other. And so the reason for the fully connected graph at any point in time is that as long as a robot can see some other social agent nearby, it's probably important for that robot to consider that social agent is there, because that can change in a way what's going on. Even if that other agent is not explicitly sort of engage with the robot at that specific point in time. Now, you're right in that intuitively what's going to end up happening, right, is that this allows us to have a wide variety of edge features that, we can sort of reason over time as we need to. But that's sort of I think the practical value of it is that, our edges are not necessarily one thing we have or we don't have it. Actually, you can think about it as a feature vector that has many things that we may care about. And this is important because, well, this context, as I mentioned before, is so many things that you don't want to lose that flexibility when you use this graphs abstraction.
Thank you. That's clear now. Thank you. Very interesting. Any other question for Marynel? I guess I had another one, which is a bit more on the applications. I mean, here, a lot of times when I see HRI applications, I see people worrying that the robot really doesn't hurt people, but also is kind of not disturbing people. But have you also thought about applications in which you want the robots to influence the people to do certain things? For instance, I don't know, you want to regulate a crowd, move a crowd in some direction. I don't know, I'm thinking about situations in which you want to avoid people being too densely in a particular place or...
Yes, so I can tell you, for instance, right now, we have this robot that we're deploying in public. A lot of the problems we're thinking about in many ways are things that I thought about as a PhD student at CMU. So if you have visited CMU's campus, Reed Siemens has been deploying robots there for a really long time. And so when you enter, for instance, Newell Simon Hall, there's tank right at the entrance of that building. And me as a PhD student, I thought it was really cool that I was just there and people could interact with the robot whenever they wanted to. But also that robot tried to say hi to me all the time. And so at some point in time, I actually felt bad just ignoring it. It's like, I would just pass by because I knew everything about it. I didn't want to interact with it, but the robot still kept saying, hi, hello. And so one of the interesting questions with these robots when we deploy them in campus is, we want this robot in a way to maximize the number of people that interact with it, but only if people actually care about it. And so this now brings up interesting questions of, can we predict when someone is passing by, are they intending to interact with the robot, or are they, kind of busy? This is someone that we shouldn't really try to start an interaction with because probably we're going to bother them. And so we're using these GNNs to make this type of intent prediction. And then the next step after that is basically to start thinking more from a behavior control perspective on what behaviors can the robot show to maximize interactance subject to not bothering people. And this goes sort of very quite at sort of the space you were thinking of, how do we influence people, right? The people that are just wandering around that we wouldn't bother, those are people that we want to influence to come and interact with the robot. We want to show that the robot is open to them, that is there, for them to interact with it. And actually coming up with the right behaviors to do this is really, really hard. Because there's a lot of nuances in terms of how people look, what they're doing, how they're moving. And so I think really the only way to do it well is actually learn from experience, by trial and error, basically. Come up with a controller that hopefully can improve the decision making of the robot in terms of deciding, oh, is this a person that I should really try to engage or not? And so that's sort of where we're coming with this robot. And this comes up in HRI all the time, because in many ways, we want to use these robots to do positive things for the world, and more often than not, that implies sort of influencing people one way or another.
Thank you. That's indeed a very interesting field of research. All right. Let's see if there is maybe a last question for Marynel. I don't see any in the chat, but maybe somebody wanted to ask directly. I think you left your email in the, at least in the title slide or in the final slide.
Yeah.
Yes.
If you have any questions, please feel free. Yeah, to reach out. Also, if you're interested in this type of graphs and graph neural networks in applications related to HRI, I would love to hear about how you're using it. And the reason for this is because, I didn't make up graphs. Probably many of you are using graphs for many things, and data-driven techniques are in many ways opening up new opportunities in many cases to do things better than we could before. And so I think for me, one of the advantages of starting thinking about context in this way is that potentially we can expand some of the work that we're doing to other areas, but also benefit HRI in the long term with advances that have come up in other related spaces. And so, yeah, if this is something that interests you, please contact me. It would be great to hear from you.
Thank you, Marynel. Thank you again for the great talk, and good luck for the next steps. And thank you all for participating, and see you all next week for the next talk.